Welcome to this talk highlighting some key advancements in thermokarst research, along with an assessment of three key challenges that we think will be sort of defining features of our work in the coming decades. First, I want to highlight the importance of permafrost carbon within the climate system. This schematic shows the magnitude of the permafrost carbon pool, storing about twice as much carbon as is in the atmosphere, certainly storing more carbon than global vegetation biomass. Another key point about the permafrost carbon pool is that this is a pool that is in dynamic exchange with the atmosphere. So any changes to the size of this bubble or pool under coming climate change will affect the magnitude of the atmospheric pool. And an elephant in the room that I want to acknowledge right away is that while we are interested in the role of permafrost in the climate system, we can't lose sight of the fact that these permafrost emissions are far dwarfed by anthropogenic emissions. This figure shows the spread of human emission scenarios as a function of temperature anomalies. The strength of permafrost carbon emissions can be assessed by running climate models with and without permafrost. So the difference between these two white lines represents the strength of the permafrost carbon feedback to climate. And while it demonstrates that permafrost does in fact have an influence on climate and triggers temperature change, it definitely does not come close to the role of human emissions. And so we need to continue to vocalize and message as a group of scientists and researchers the importance of mitigating and reducing anthropogenic emissions as our key mechanism of keeping permafrost frozen and keeping that carbon in the ground. And yet we do know that climate models currently are lacking in that they only represent gradual active layer thickening. Of the models that do account for permafrost at all, none include more abrupt or thermokarst processes. And this is what I want to focus on for much of my talk today. It's these abrupt thaw processes that affect the most carbon dense and carbon rich soils. At least 50% of the permafrost carbon pool is stored in the 20% of the permafrost region that is vulnerable to abrupt thaw. So disproportionate amounts of carbon storage in relatively small regions that are prone to these abrupt thaw or thermokarst processes. And these truly are exciting times for thermokarst research. And I've just listed a few reasons here why. We are witnessing an explosion in the geospatial technologies that allow us to monitor and track features over time. I'm just going to show one great example from Guido Grossi's work in Russia, kind of as a demonstration of the power of what we can do by harnessing new and improved approaches in remote sensing. We are also seeing more and more communities and networks come together to share data and to share resources, often at international scales. And this is also extremely exciting. And yet we do face some key challenges that we think will define the coming decades of thermokarst research. In this talk, we outline three key challenges. The first challenge is that technological advances are incredible and often very sexy, but they often don't improve or aid our process level understanding. It's the local observations, the hard-earned field measurements that make large-scale work more powerful. We need to continue to invest and value this field work. And we need to find ways to foster the mutual benefits of this basic local measurement scale with some of this larger scale work that often is harnessing and capitalizing on technological advances. We can find that happy interface where we can leverage both at the same time. The second challenge is this vexing issue of how to embed fine-scale processes like thermokarst into large-scale models. And this truly is a challenge that needs to be solved in the coming decade, or at least we need to keep marching down this path. This black box is meant to visualize the scale of a half-degree grid cell used by many climate models. I would need to magnify the area of a typical thermokarst feature by 1,000 to get to the point where we could even visualize a thermokarst feature within this scale. So this is like an ant staring up at a dinosaur of a climate model. On the other hand, recent tracking of thaw slumps shows that we do have thousands of these thaw features developing in some permafrost regions. In this study, 50,000 thaw slumps were detected in a region of Northeast Siberia. So you could imagine sort of combining or smushing those 50,000 thermokarst features into one red cell in this black box. Then it would amount to a fairly large area of thermokarst combined that we would need to represent within our climate modeling scenarios. And yet we still lack a framework for how to move forward on accomplishing this. We need to be able to first model the consequences of thermokarst at a single site or at a single ecosystem. We need to have that mechanistic or process level ecosystem information before we can start to scale up the effects of thermokarst to regions or across the Arctic. This is a great approach for tiling, which, for example, in climate models is often used to represent global fire distributions. But we really need to rethink this tiling approach in a dynamic way. And I think thermokarst is a great example of how we need to do this rethinking. Thermokarst triggers such complex changes in land surface disturbance, vegetation, and hydrology, and all of those processes interact with one another. So our tiling approach really needs to represent those interactions in a dynamic way. Using a simple inventory model, we ask the question, how does abrupt thaw generalized into 3 different kinds of classes of thermokarst compare to gradual active layer thickening? We use this inventory model to answer that question. And what we found is that abrupt thaw emissions represent about 45% of carbon emissions generated across the circumarctic by gradual thaw. But because of very high amounts of methane emissions associated with those abrupt thaw processes, those carbon emissions created a similar amount of climate feedbacks. In other words, when we accounted for the strong radiative forcing of methane, abrupt thaw climate feedback was almost equivalent to the climate feedbacks of gradual thaw. So this suggests that by not accounting for abrupt thaw, we might be underestimating the climate consequences of permafrost thaw writ large by as much as 100%. But we currently lack an understanding of how to even interpret these fluxes. Can we add the fluxes together of abrupt thaw and gradual thaw? Do we simply just add those numbers together? Well, no, we can't do that because we know that there is some overlap between these boxes. And so that sets up the stage for some potential double counting in our models. But a key point is that we really can't be consistent with understanding or predicting water, carbon, or energy fluxes, nor can we understand uncertainty estimates until we properly embed thermokarst in Earth system models using some kind of approach. And finally, a third key challenge, and perhaps this is the most important, is that we need to recognize that much of the history of permafrost research, like much of high latitude or Arctic research, is based in a history of colonialism. And this needs to change, and it is changing. It's changing because it's the right thing to do. And in that change, we will become better researchers. better mentors for our students, and better people. Co-location is a start. We overlaid the location of permafrost measurements with the location of northern communities in the North American, taiga and Arctic regions. These are permafrost measurements that were found in the published literature, so peer-reviewed literature only. What we found is that 75% of communities do not have any permafrost measurements made within 50 kilometers. So if we want to create use-based science, if we want to create actionable science, this needs to change, and it can start through co-production of knowledge and co-location of measurements. This is a great example of that kind of research, where researchers are making observations and monitoring the type of permafrost thaw leading to erosion and landslides in the vicinity of different communities in the Northwest Territories of Canada. This is a great example of action-based or user-based science. We need to help communities understand and predict the risk of permafrost thaw. And risk is not just a product of permafrost thaw probability. It's also incorporating the consequences of that thaw. So we need both pieces to be able to create risk-based assessments that northern communities and northern stakeholders can use. We need to start assessing the socio-ecological consequences of thaw, not just creating maps of where thaw is occurring. So thank you for your attention. I hope these issues or these vexing challenges for thermokarst research has been interesting for you and creates a seed of discussion and more thought. Please join our session on Friday if you would like to join in on that dialogue, or please reach out to me either through email or social media so we can continue the conversation and continue to tackle some of these really important challenges that will define permafrost research into the future. Thank you.